Hello everyone, welcome to the new video. Today we'll be talking about this paper which is titled as Line Large Scale Information Network Embedding. This is from researchers from Microsoft Asia, Peking University and University of Michigan. So this is one of the early works and foundational papers in the domain of machine learning with graphs, or can also be thought as network learning, where the idea is to kind of represent the components of graph or sometimes the graph itself in some high dimensional space in a vector form so that it preserves the semantics that were there in the original graph as well, such as neighborhood properties and relations. So this paper got published somewhere around 2015 in World Wide Web Conference. So let's start with the abstract. Also, before we start, you might hear some disturbance due to the construction work that's going on the second floor of my house. And yeah, I cannot help that. And it's really hot outside for me to go in the car and record this thing. So I hope you'll understand. Okay, so moving on. This paper studies the problem of embedding large information networks with low-dimensional vector spaces, which is useful for many tasks such as visualization, node classification, and link prediction. So yeah, you have a very large information network such as communication network, transportation networks, airline networks, and so on and so forth, where you can expect easily million to billion number of nodes in that graph. So the idea is, can we embed that graph in some low-dimensional vector space? Now that could be about embedding the graph or embedding the lexical units such as nodes or edges in that graph. Because once you have some low dimensional representation in a vector format, you can train a machine learning model to do tasks such as node classification, where given a node, you want to know whether it belongs to this category or that category. Or you might even want to do link prediction, where the idea is, let's say you have two nodes, you have the embedding for this, embedding for this. You want to know whether there should be an edge between these two nodes or not. This is a prominent use case in social media networks such as Facebook, where you would have seen the feature that Facebook implements, which is, do you want to be friends with this guy or not? That kind of a suggestion. So that is where they are typically doing a link prediction between the nodes, which are users in that graph. Okay. So in this paper, we propose novel network embedding technique called Line. So it is suitable for any kind of graphs. It could be weighted, unweighted, directed, or undirected. And the idea is to kind of preserve the first proximity neighbors as well as the second proximity neighbors, which would kind of preserve the local as well as the global context in that network structure. So we'll see in a bit to what first order proximity and second order proximity is as we proceed forward in the paper. So apart from proposing this idea to how to do this, they also propose an edge sampling algorithm that improves the efficiency of the algorithm while inferencing as well as training. So yeah, let's move forward. So they say, naturally, the local structures are represented by the observed links in the networks, which capture the first order proximity between the vertices. So if you see this graph, we can observe a strong relationship happening between node 6 and node 7. So all these adjacent connections that happen to be for a particular node, let's say V, in this case, let's call 6 as V, would be called as first order proximity. So this corresponds to the local context within the graph around a certain node V. So if you want to capture a little bit of global context, it might not be necessary that the nodes have direct link between them, such is the case in this graph between 5 and 6. But if you see the neighbors that they share, which is 1, 2, 3, and 4, all of them are same. So based on this idea, you can also conclude like 5 and 6 are also similar. So this is what second order proximity means. So now you can think of analogy of second order proximity that happens in word to vec kind of algorithm, where the assumption is like the words that have common neighborhood would be close enough in that high dimensional space, which means they would be more or less similar. Also, if you want to think this in the context of social media networks, it could be thought of as, let's say, people who share many common friends are also likely to share same interest or become friends, which is the use case for link prediction. So yeah, this is a prominent behavior that happens in general networks, hence it makes sense to also incorporate that as an objective while identifying the embeddings. Let's move forward. So now let's define the problem statement formally. So there are a couple of definitions that they define. The first is information network. So information network is nothing but a graph G that has V vertices and E edges, where edge essentially represents the relationship between two vertices or two data objects. So let's call that edge E as U, V because it exists between U and V. And you might have some weight W, which is greater than 0, which kind of indicates the strength of the relation that two objects hold. So in case the graph is undirected, then U, V and V, U both mean the same thing, unlike the case if graph is directed. Okay, that's the first definition. The second is first order proximity. So this kind of captures the local pairwise proximity between any two vertices that occur to be in that graph. So the weight that you define between two edges that are adjacent to each other is called the order of proximity that exists between two data objects. And in case if there is no edge that is observed between two vertices, then you call the first order proximity to be 0. So in real world networks, you would find like very less number of connections would have first order proximity, but that doesn't mean these are not similar, because if you observe the second order proximity for those nodes, which was in the case of the example that we saw, where two nodes were not connected but they were sharing 1, 2, 3, 4 as their neighbors. So from that concept, those nodes were similar. So here's how they formally define second order proximity. It exists between the vertices u and v. So let's say this is the weight distribution that you have from node u to all the other vertices that are connected to it, where u is nothing but the current node that you're considering. So in case you consider another node and make this similar set that goes to or comes to u and v, then you call second order proximity to be 0, which means they don't share any common neighbors. Okay, the last definition that they define is large scale information network embedding, because ultimately we aim to get the embedding representation for every node in the graph, right? So let's say we have a graph G which has v vertices and e edges. So the aim is to find for every vertex that belongs to capital V set to get a low dimensional representation RD. So it's a d-dimensional representation over real numbers. So we want to learn a function fg that would take in a vertex v and get me a d-dimensional real representation for that vertex, where the dimension, which is d, is much less than the total number of vertices that you have in that graph. So this has to be the case because the plain vanilla way of representing every node could be of length dimension v, where you just one hot encode the indices, which are the neighbors, and rest you can put it as 0. But that would be really sparse and would consume a lot of memory, which is the case of TF, IDF and bag of words kind of model. That's why we had these embeddings kind of systems, which are dense and meaningful representation. So yeah, similar is the case over here. And this dimension has to be learned in such a way that the first order proximity, which means adjacent relationships, as well as the second order proximity, which means not adjacent relationships but sharing the common neighbors, has to be preserved. If it's there in the graph, it should also reflect in that d-dimensional space. So yeah, these are all the definitions that they define formally. Now talking about the model, which is line. So for each undirected edge I, j, we try to find the joint probability of the vertex vi and vj as follows. Okay, so this is a sigmoid function that you apply over the dot product of vector representation of the adjacent nodes, where each of them is of d dimension. So this would return a squashed value between 0 and 1, telling about the similarity between two adjacent nodes, where the closer this value is to 1 would mean very high similarity between the nodes. So this is what our model is supposed to output. So the value against which we evaluate this number to calculate the loss is the empirical probability, which we define as this, where wij is nothing but the actual weight between the nodes, and you divide it by a summation of all the edge weights that you have in the graph. That way you also again normalize it between 0 and 1. So this is the empirical probability distribution that we have, and this is what our model is saying. So the objective function that they define is a distance metric over both the distributions. So what better than applying KL-Divergence, because you have two probability distributions and you want to kind of measure how one probability distribution is different from second. So this is the final O1 objective that they apply, where O1 stands for the first objective, which belongs to the first order proximity. So here you kind of pull out every edge that exists in the graph. What is its weight that you have, which is the empirical probability, and what is the probability that a sigmoid is giving. So you want to match this as much as close to this. So that way you're kind of pushing the generated distribution more to the actual distribution. So let's talk a little bit about how did the KL-Divergence term, which has a different formulation if you see it visually, boils down to this cross entropy term. So if you recall the KL-Divergence term between the distribution P and Q, it is written as summation over all the i's, all the horizontal axis points that you have, P of I log of Pi upon Qi, where P and Q are two distributions. So let's simplify it a bit. It can be written as summation Pi log of Pi minus Pi log of Qi. So if you see this first term, there's nothing but minus of entropy of distribution P, and then you have minus Pi log of Qi. And now this term is nothing but the cross entropy term between P and Q, where P is the actual distribution and Q is the estimated distribution. So this resolves my KL-Divergence term from this to h of P comma Q minus h of P. So here HP can be seen as a constant because this is true distribution and it's not gonna change. So this resolves KL-Divergence term to the cross entropy term. So if you see this formulation again, that's what they have written as well. We omit some constant and then you have this KL-Divergence equivalence to the cross entropy term, which means minimizing cross entropy would also minimize KL-Divergence between two distributions. Okay, moving forward. So now talking about second order proximity with line. So this is also applicable for both directed and undirected graphs. So they have assumed directed graph for doing the formulation. But if you notice, undirected edge can also be considered as a two directed edge with same weights, which kind of nullify and you get a undirected graph. So that is kind of a easy conversion that you can do from one graph to another. So in this case, you get two identities for every vertex. One is the context and one you can think of this as a vertex of interest for which we are trying to get the embeddings. So let's call the vector representation of these two identities as UI and UI dash. UI if it's treated as a vertex, whereas UI dash if it's treated as a context. So the idea is to maximize this probability. So the idea is to get the probability of given a vertex, how probable is the context. So for this they apply the softmax function over the dot product of both the vector representations. And let's say you have V nodes in the graph. That's why you have this expensive summation happening in the denominator. So with this you get a probability distribution across all the edges that sum to 1 that go out from Vi. So again the idea is similar. We should know what the actual distribution or the empirical distribution was, and similarly we'll apply the KL-Divergence distance for that distribution, which is the empirical distribution, and the one that is estimated by our system, and we want to minimize this thing for all the nodes in the graph. And this lambda, what you see right, is an importance parameter or the weight that you assign for the node Vi. So in this case I think they have taken it as a node degree. Yeah, this is the degree of the vertex I, but you can think of applying more sophisticated scoring schemes such as PageRank. So here the idea is to tell the importance of the node to the algorithm for which we are trying to get the embeddings. So again, as we saw in first order proximity, KL-Divergence can be reduced to cross entropy, which is again the case over here. For all the edges that you have between I and j, given the node Vi, you want to know what is the node Vj with what probability. You take the log of that. So this P2 Vj given on Vi is the estimated distribution, whereas this Wij would be the actual distribution. And we are trying to learn a function such that the actual and the estimated distribution resemble each other. Okay. So to represent every node in a final vector representation, they concatenate the embeddings that you get from both the methods. So one is capturing the local or the first order proximity. The second one is capturing a little more global, which is also known as second order proximity. You get the embeddings from there, let's say V1 and V2. You concatenate them, and that is the representation for every vertex. Okay. So you must have already thought by now about the optimization process, because the denominator of the softmax is a summation over entire vocabulary or entire number of nodes that you have in that graph. So typically the graphs are millions and billions of nodes. So the summation is really costly. So they apply a classic technique called negative sampling. It is again one of the optimization things that is also applied in Word2Vec, where the idea is pretty simple. Instead of applying a softmax over entire vocabulary, let's say V, you do a sigmoid over every node that you have in the output, which is a pretty faster solution compared to calculating the summation and doing the softmax. So let's say if I give my model UI, it goes to a network, and at the output I have a d-dimension or the v-dimension representation for every node in the graph. And let's say I'm optimizing on one of the neighbors that I have, let's say uj, and which is this one. So I have a value 1 over here and 0 for everything else. So individually my model will have to optimize on sigmoidal, saying this is close to 0, this is close to 0, and this is close to 1, this is again close to 0. So that will have to optimize on every node. So to approximate this procedure, what negative sampling suggests is that you sample some k random samples that are negative and use only those things while doing the backpropagation. So let's say if my v was 4, 1 is the truth sample. Let's say if my k value is equal to 1, then I would randomly select any of the nodes, let's say this or this. So let's say these are my two activated nodes. I'll use this and backpropagate and adjust the weights of my network for the further iterations. So this kind of approximates the performance and is equally good, at the same time reduces the training time by a lot. So yeah, this is the objective function for that. So this is the positive sample, which is log of sigmoid over the representation of the positive sample, which is the one of the neighbors, and for UI, which is my input. And let's say if I do k negative samples, so I do a summation over here, I do a log of that with the dot product of both the node representations. And I would want to minimize this objective. If this is going close to 1, which means if it was 1 and we are saying it as 1, then this value would go to 0 because log of 0 is 1. So if you see this term, if dot product goes to 1, negative of that applying a sigmoid over that would result in something that is close to 0 and would result in minus of some log value. So that way again this entire thing is minimized, which is the objective for the second order proximity. Okay. So yeah, this is one of the optimization that they apply. But there is one more thing that they improve, which is that if you notice you have this wi term which is multiplied in the second order proximity. So these values could range from very high values to very low values and will have a very high variance, which will kind of impact the model's convergence rate by finding it hard to get a good learning rate. If you choose a high value of learning rate based on the value of wij, which is small, that would hamper the cases where wij value is really high, as that would result in exploding gradients. So to overcome this, they propose something that's called as edge sampling. So the intuition is that if we have the weights that are almost same, or maybe for that matter exactly same, then it's very easy to choose the learning rate rather if the weights shuffle from very low values to very high values. So for that, what they do is they unfold every weighted edge into multiple binary edge. So let's say these are two nodes and the edge weight is 3. They would dissolve this to like having 2 nodes and 3 vertices with 1 weight each. So yeah, that's what they have written. An edge with weight W is unfolded into W binary edges. So this way we have achieved one thing, which is that the weight for every edge is 1, which is all same. But clearly you can see like 1 goes to 3, which means there would be a significant increase in the memory as well. So to resolve this, they sample from the original edges and treat only those sampled edges as binary edges. And the sampling probability is proportional to the original empirical edge weight that you have. So since you are doing an expansion at earlier stage, there is no impact that happens to be at overall objective function. So yeah, this was one of the optimization that they introduced. So yeah, I think now we are done with the paper. So yeah, as I said in the starting, it is one of the early works that came out around 2015. So after this or around this, I think DeepWalk also came, post that Node2Vec also came. So there have been a lot of improvements that happened over the years. A couple of which I can directly think of are, let's say, line has 2 objective function. One is to optimize on local proximity, which is first order proximity. The second objective, which is O2, is on optimizing on the neighbors, is called second order proximity. And the vector representations that you get, you basically concatenate those things, and that is your final representation for the entire node. Whereas if you see DeepWalk, it is based on random walk scheme, where you kind of sample nodes from the graph using some random walk strategy, and it could be of length L. That way you're kind of going more deep in the global context to different areas of the networks as well. Rather than where in this paper, they just focus on first and second order proximity. Then moving on to Node2Vec, which is again an improvement over DeepWalk that helps you kind of do a trade-off if you want to explore locally or do a global search, which again is kind of an improvement over line as well as DeepWalk. Because in line, if I talk about local context, you're thinking of just one hop neighbor and global being the second hop neighbor. And in DeepWalk, you are still unsure how will the random walk behave, whether it will be just exploring the local neighbors or it will be going really deep. So that is the privilege that you get in Node2Vec, where you can control what is the smallest proximity that you want to explore and what could be the largest proximity that you can explore. So this to me kind of seems to be the best of both worlds of line as well as DeepWalk. So if you want to explore more on how DeepWalk and Node2Vec exactly works and the mathematics behind those algorithms, I've already made a video on those 2 papers. Do check them out in the I button. So yeah, having said that, it was a pretty interesting read. If you like such content, make sure to hit that like button and subscribe to the channel. Also share it across with the friends to whosoever is interested in such content. I'll meet you in the next one. Bye bye, take care and stay safe.